Okay, let's do it. Start. So last week we started talking about stack-based buffer overflow or sequential buffer overflow because the problems we're looking at are caused by functions like string copy, memory copy, gets, fgets. So they read some data from some input, could be terminal, could be files, then put the input into a buffer. The problem is the buffer may be smaller than the data we are reading there, so causing some out-of-bound write there. We talked about the brief history of buffer overflow, information, C function we need to execute, several C calling conventions. Here you need to pay attention to 32-bit and 64-bit. 32-bit, we use stack to store the parameters. 64-bit, we use registers. Then I showed you multiple examples of overflowing local variables. So today we are going to do something more fun. We are going to not only overflow some local variables, we will overflow the return address on the stack. If you remember, on the stack, when we enter a function, there are parameters. There are return address. One return address, then there is a saved stack string pointer, saved EBP or RBP, then we have local variables. So today, we will focus on overflowing the return address. The return address is an address. An address in C or in system is basically a pointer. It points to code, right? It points to code when the function returns, the CPU is supposed to execute from there. So this pointer is called a code pointer. There are many other pointers on stack, and when you program, there are many other pointers. They're not necessarily all code pointers. Some of them are data pointers. Like the saved EBP is actually a data pointer. It points to the previous function's stack frame. But in that data structure, there is also a return address. In C, you also have function pointers. So function pointer obviously is a code pointer. So we're going to say how can we overflow the return address so we can execute a function. We will also say if we can execute a function with parameters and whether we can chain multiple functions together. Then, if we have time, we will talk about what if we do not overflow return address to execute a function, just to execute arbitrary piece of code. So you probably read from news, somewhere arbitrary remote code execution, RCE, remote code execution, RCE bots. So this is related to that. So hopefully we can talk about that. Then we can put some arbitrary code there, then execute that. Okay, so this will be our very first control flow hijacking attack. So what we discussed last week was a data flow attack, not a control flow attack. So here we are going to hijack how CPU execute the sequence of instructions. So it's control flow attack. Let's revisit the return address and the function frame pointer again. Hopefully you know much more about this after the homework and everything. So in the function prologue, at the very beginning of the function, the compiler will instrument some instructions to save the EBP or RBP, right? So that is called the frame pointer. It is actually a data pointer. It points to the previous function's frame. Then it will also save the EIP or RIP, which is the next instruction to be executed, the address of that, when the function returns, right? So in my slides, I called them just the RET, return address. So that is basically a code pointer. So they are stored on the stack. And there is no mechanism in the programs we are looking at today to prevent a bug from overwriting those important data. Okay. So you saw that last week when you overwrite that local variable, you can keep overwriting. You can keep overwriting the return address. You can keep overwriting the saved EBP. There is nothing to prevent us from doing that. Next week, we're talking about some modern defense system. So the idea of this stack-based buffer overflow here is to overwrite the saved EBP and RBP value because they are unstacked, because they are in memory. So this is still a memory corruption attack. So the attacker's goal is just to change the value. So then later, when the program, when that function returns, it will not return to where it is supposed to return. Where it is supposed to return is pushed by the call instruction onto the stack. We overwrite that. So it will execute some code, some other code. So this is a very common vulnerability in C and also C++ programs. If you are reading the classic, the C programming language book, even the classic book written by the authors of the C programming language, the examples in the book have this kind of a box. Okay. So this is the first example we will look at today. Super simple example. We don't have a local variable there anymore because we are not trying to override the local variable like last time. Main function still take 2 arguments. Then it print out the address of print flag. So print flag is a function I already embed in this program. Of course, when you hack other programs, the developers of those programs will not conveniently give you a print flag, obviously. That's why in the second half of today, we are going to learn more general techniques. Let's assume right now we have a print flag function, and we also print out the address for you. Okay, so you know the address. Then we call the vulnerable function valfoo. Valfoo has a local variable buffer. We're asking for 6 bytes at a second level. Not necessarily the compiler will give us just the 6 bytes, maybe more. That's why we need to look at the disassembly code to see how much the compiler is really giving us. Then we have another gets function. So we're not using, previously we were using string copy. So here we're using gets. They are all vulnerable functions, okay? I'm trying to introduce more vulnerable function here. But the idea of gets is to get a value from the terminal, from the std input. Then it just returns. That's it. So then after it returns, the program calls another printf ipt the full. Okay. So if you just run this program, it will just show you the address. Then it will print out ipt the full. That's it. So let's run this program. Overflow. Return 1, I believe. So when we run this program, it will get some input from us. It will first print out the address of printf is that address. Then it waits for our input. Then we just input something from the buffer. Then we just press enter, then print out ipt the full. So if you are trying to hack something, obviously you will try to give it all kinds of different input and to say how it behaves, right? So if I give a much longer input, it eventually generates this segmentation fault. The reason is when I give that much input, it will overflow the return address and also save the EBP. So when that valfoo, when that main function, when the main, actually valfoo function. When valfoo returns, it will return to a random place because I give it some garbage there. And that random place obviously doesn't have legit instructions. So that's why we get a segmentation fault there. So how do we exploit this? A little bit about gets. So gets will read a line from the standard input. This program right now, the standard input is just the terminal. Then it takes one argument, which is the address of the buffer where you want to save the input. It will put the input into that buffer. and it will add a null byte at the end, and it will only stop reading until it finds a new line or end of file. Okay, so it doesn't care how long your input is. It will only look for a new line or end of file. So you can see there is a similar pattern to the string copy we talked about. String copy will keep copying until it finds a 0 there, right? Even string uncopy, which gives the number of bytes you want to copy, may still have buffer overflow because the number you give there may be bigger than the size of buffer. So the function itself doesn't check whether there is a buffer overflow. Most of C functions don't do that. The library functions don't do that. So obviously this is not safe, and you should not use this when you write your programs. Okay, the compiler actually will warn you should not use those functions when you program in C right now. Then let's take a look at how this actually overflow everything. Similar to what we have last week, but the size here is different. So let's do that again. Before we enter val foo, we enter the val foo through function main. Main function has an instruction call val foo. So we enter, then we are about to execute the very first instruction in val foo. So at this point, the stack will have the return address there. On top of the return address, we may have parameters, but this val foo function doesn't take parameters, so no parameters there. So just the return address there. ESP points to the return address. Then we are going to execute the end BR32, which is something we can ignore for now. Then, first of all, that function doesn't really change the stack. So we can ignore that for now. That's actually a security feature. But that security feature doesn't stop the tag we're going to talk about today. Then the first instruction we execute is push EBP. So EBP is, the value in EBP is saved to stack. So ESP points to the saved EBP, and the EBP still points to the previous function's frame. Then we move ESP to EBP. So now both EBP or ESP and ESP points to the same place, which is the saved EBP. Then we subtract ESP 18 in hex bytes, that is 24 bytes in decimal. So ESP moves down, EBP stays there, okay? Usually during the execution of this function, EBP will stay there, but ESP will be moving around. If this function calls another function, obviously, EBP will be changed again. Then we subtract this again. Why the compiler is doing this, I don't know. Well, obviously, it can be optimized, but the actual disassembly we're looking at is like this. That's why I'm showing you that. Then we have another 12 bytes. So in total, we have 36 bytes. So from where ESP points to and where EBP points to, in between, we have 36 bytes. Then we load effective address EBP minus E to register EAX. E is 14. So we are loading the address EBP minus 14 to the register EAX, which means between EBP minus 14 and EBP points to, we have 14 bytes. That is where our buffer is. So at the C code level, we asked for 6 bytes. Okay, the compiler actually gave us 14 bytes there in this case. Okay. Then how do we know that's where the buffer is? Because next we have a call function to call, this one is gets. So here, you do not really say gets here, you say val foo plus something. That is just a placeholder. So at runtime, it will eventually be changed to gets. So the parameter for that is on stack, and the parameter is in EAX, because before that there is a push EAX, and EAX has a value of EBP minus 14. Right? So the buffer is at EBP minus 14, which means if we overwrite 7 bytes, we input 7 bytes, we're not going to overwrite something. The buffer is 6 bytes in C code. It's actually 14 bytes at runtime. If you put 6 bytes there, 7 bytes there, 8 bytes there, you're not going to overwrite anything. But you put 15 bytes there, you're going to overwrite the saved EBP, right? If you put 16 bytes there, also save the EBP. If you put 19 bytes there, then you are going to write into the save the return address. Okay. So today we only care about overwriting the return address. Next week we'll talk about what if we cannot overwrite the return address. We can only overwrite the saved EBP. We will still be able to achieve what we can achieve this week. Then after this call, we're going to add 10 to ESP, so ESP moves up. Then move 0 to EAX. Then val-foo will just return. So when val-foo returns, before return, it executes the leave instruction. And the leave is basically move EBP to ESP and pop EBP. So let's say move EBP to ESP will make sure ESP has the same value as EBP. So both of them will point to the saved EBP again, right? Then we have pop EBP, which means ESP will move up because it's a pop. ESP move up 4 bytes, and the EBP will have the register EBP will have the value which we stored on stack, which is a saved EBP. Okay. Then after that, the next instruction to be executed is just return. And return will just pop whatever ESP points to EIP. Okay. So then we are going to change this return value to the register EIP or RIP, then ESP also moves up. Okay. So how do we overwrite this? Very simple. We just need there's 24 bytes there. The buffer is at where? The buffer is at here. 14, okay. So we need 14 bytes. We want to overwrite return, right? So how many bytes of garbage we need before that? Who said that? 18. 18, right? 14 bytes for the buffer itself. Another 4 bytes for the saved EBP, which we don't care about the value. That's why we have 18 bytes of garbage. Right? So if we write 18 bytes, then we are going to overwrite the return. So the function returns, we will get a print secret. So let's take a look at this. So this program takes input from standard in. That's why we need to pipe data into it. So we just, let's say we have 18 bytes of garbage. I just use A there, 18 times. Then we're going to get the address of that print secret, which I don't know the address. That's why we need to run the program first. So when we run this program, it gives us the address. And this address, as you can see, will not change. No matter how many times we run this program, this address doesn't change. In modern systems, in your laptop, phones, when you run a program, every time it runs, those addresses actually will change. Even the kernel will change its address, but we're only at boot time. So this is a technique called address-based layout randomization. It is implemented at the kernel level. And for now, we disable this feature. Later, maybe 2-3 weeks later, we're going to enable that feature, and you will still need to defeat those differences. Okay, so now then we can pipe this into the program. The address we have is 60, 62, 56, no, 55, 56. All right. So when we do this, we get the flag, but we still get a segmentation fault. Okay. The reason we get a segmentation fault is we overwrite that saved EBP. And that save the EBP is something the main function will use. And because of that, eventually we get a segmentative input. So that is the address of print secret. But let's say we do an obj dump here. This is a print flag function. As you can see that the print flag function has an offset of 1260. That is not the runtime address for it. It's just the offset. And the runtime address, we saw that was 6260. Okay, so there is a base, and that base is determined at runtime by the kernel. Then there is an offset, it's 1260. If you minus that offset to this runtime address, you will get the base, which will be 5000, right? That's obviously the base of that segment. So, is there any other address we can jump to? Instead of at the beginning of that, 1260, we can still get the flag. So we're trying to jump to 1260 there. What if we jump to 126E? What will happen? 1 byte after that. So if we jump 1 byte after that, we will not be execute this instruction on the BR. Instead, we will be executing this, right? I don't know if that is a valid instruction. So maybe we will get a segmentation fault, we will get an illegal instruction fault. If we jump to here, maybe the same thing. Here's it. But what if we jump to here? We just skip the very first instruction. Should we still get a flag? No? You said no? Why?
Did we overwrite EBP just?
We did overwrite save the EBP, but that save the EBP has not been used, has not been dereferenced yet. Yeah.
I think it would work.
Okay. It would work. Okay. So let's try that. Right. So let's change our exploit a little bit. Instead of a did I share screen? Oh, I share. Okay. Instead of 60 here, let's do E. When we do E, actually works. F doesn't work. Okay. If we do 71, it doesn't work. 70 doesn't work, but 71 should work, like you said, right? So 71 actually works. So when we do 6E, actually it also works. That's because this one is somehow a valid instruction. I don't know what that is. Let's find online disassembler. Okay. I can also use GDB to do that if no system blocks this. Say disassemble. Oh, no, this tool cannot do it. Let's just debug this. GDB. So let's set a breakpoint at, doesn't really matter. Let's say set a main function. We just run this. We don't really need to run. So your X command is exam. We're trying to exam the instruction. We exam, let's say, 5 instructions. Add the address. What is the address? 56, 55, 62, 60. Yeah, so here. So instead of exam this, we start with 6E. We skip 1 byte. You can see when we skip 1 byte, those 3 bytes actually is a valid instruction, and it's a null instruction. It doesn't do anything. Okay, that's why it still works. But if we skip 2 bytes, if it's 2 bytes, those 2 bytes, maybe adding another byte, becomes a push instruction. And after that, there is a set enable interrupt instruction. And because of that, this is first of all, this push may be a little bit dangerous. Maybe this one is what triggers the segmentation fault and why we do not get the flag there. If we do 7-0, it will be similar. Yeah, I think it's because this instruction. This should be a privileged instruction. We cannot really execute this instruction and use that. That's why we get a segmentation fault there. So that is basically how we override the return address and have your first control flow attack. You can also write exploits, write Python code to do this using the Pound tool library, which will make things more automated. So in our previous example, you run the program, you get the address, then you run the program again. So technically, you should be able to receive that address from the program, then send out your exploit to it, right? Then we can do that with this Python code. Same here. This program, we do not have any command line arguments, so it only have the pass. So previously, the example I show you has a pass and also command line argument. Then we will just use this function receive until. It will receive data from the program until it gets this string. You need to convert this string to binary, B there. So the address of the print flag is 0x blah blah blah. Then after that, you are going to receive a line again, and this time you are receiving the address provided to you by the program. You strip out the new line, you strip out the white space, then you convert that into that number is a hex value. That's why you converted that into integer and tell that it's a hex value. So now you have this address. Then your payload or your exploit will just look like 18 bytes of garbage, then and the 4 bytes of that address. In total, you have 22 bytes of exploit. And you use the send9 API to send the payload to the program. Then after that, you can go back to interactive mode to see that. Or if you do not use the interactive, there are other APIs as well. For example, you can use receive or timeout 1 second to do that. So let's try this as well. Let me see if I already have that on the server. I don't have anything here, so let me touch it. So when you copy code from the slides, there is something you need to pay attention to, which is the double quote and quote, because Google Slides will automatically translate the quotes. So the quotes will look different, so you need to manually fix those. Here, let's say we go here. This one is correct. This one is correct. See, this one. So Google Slides changed that. So here. Yeah, that looks good. 18 bytes of garbage, and you have to send them as binary, so that's why bytes there. Then we do Python 3 here. Then. So you can see by running this exploit Python code, you can also get the flag. So you start the local process, switch to interactive mode, and it will give you the flag. Yeah. Any questions? Okay, then I will give you guys several minutes to overflow the 64-bit version of the same challenge, it will be similar. The buffer where it is generated from the same C code, but the buffer were at a different address. Previously, it was 14 bytes, 64-bit. There is no guarantee it's 14 bytes. You still need to jump to that print secret function. Okay, so it's the same idea. I give you, let's have 5 minutes to work on this. Resolve here, yeah. So where is the buffer? 6 bytes from saved RBP, right? Okay, so how many bytes of garbage you need here? Okay, why 6 plus 4? 6 plus 8, because now we have saved RBP, not EBP. So you need 14 bytes of garbage. This one take input from std, not from command line. You finish the homework. You got the homework, so you can do this. Got it? Yeah, just keep trying. Gizra or well, this one you don't really need Gizra. Yeah. You don't have to. You can just use the simple one instead of writing a complex. Because I don't use Mac, so how do you paste that? No, okay.
RK26 with cosine use that.
Got it. Oh. Got it. Yep. How about you here? Good. So how many bytes are the address there? The address you are trying to overwrite, how big is it? It's 8 bytes. But most of you, for those who got it, you only write like 4 bytes, right? 4 or 3 bytes. Why does it work? What you are implying is your command is padding zeros. your command doesn't depend in zeros. The reason is what you are trying to overwrite is already a legit return address, right? That legit return address also have leading 4 or 5 zeros there. So yes, if it's garbage data, it wouldn't work. You basically didn't override that already existing zeros there. That's why it works. Yeah. Mm-hmm. Okay, let's keep moving. If you haven't finished this, this is your homework anyway. Okay, so now we see that we can return to a function, but the function we return to is print flag, and that function doesn't take a parameter. What if we want to return to a function that takes a parameter? How does that work? The idea is simple. You still need to override that, and you use stack to pass the parameter. So obviously, the parameter will be part of your overwriting. So in theory, it works. Right? So this is a little bit changed from the previous example. We still print out to you the function of print secrets. Now it's not directly print out to you print flag. Instead, we print you print secret. And print secret will call the function print flag. So the requirement for you is to return to print secret instead of return to print flag here. Okay, you return to print flag, it still works. You can get the flag, but I ask you to return to print secret. When you go to the beginning of print to secret, what happens is it will compare the parameter I to a hard-coded value. And we're 32-bit, so I is supposed to be somewhere on stack. I will be compared with this hard-coded value, and if they match, we print flag. Otherwise, we print IPT the full, and this one will just exit here. So the exit here is a C library function, which is also a system call. The system call's name is also called exit. So it will just quit the whole process. So this function print secret would not return to anywhere, actually. So this print secret function is not even called by anyone. You can see the main function didn't call it, Valve didn't call it. That's why you have to return there. Then let's take a look at this. This one can get a little bit confusing, okay? Let's say right now, we are at the end of Valve. We are about to execute the epilogue of Valve, okay? Not just return, but also the leave. So the EBP at this point points to the saved EBP. ESP is still somewhere down there, but it's going to be pointed to this place soon. We have buffer, and before that, a little bit higher than that, we have the return address. So now, your overwrite will overwrite the buffer. You will overwrite the saved EBP. You will also overwrite the address of print secret, right? That's a goal. And this one, let's say we overwrite it with 4 uppercase A's. 4 bytes of uppercase A's. Because that's garbage. We don't really care what we want here, right? But that matters here. Now, at the epilogue, the first instruction is move EBP to ESP. So both EBP and ESP points to this place. Then we're going to pop EBP. So the EBP will have a value of that 4 A's now, okay? ESP moves up. ESP points to the address of print secret. Then we execute return. Now we execute return. ESP will have the address of the print secret. EBP will have the value of the 4 A's, which was a garbage we put there, right? Okay. What is the next instruction to be executed now? Where? Which function?
And see.
Print secret, right? Now we are going to execute print secret. And the very first instruction we will execute is push EBP, right? And the ESP, because of that, ESP, after that return, ESP will point to this place, okay? Not the address of print secret. Now we do another push. That garbage 4A's will be pushed onto the stack again, overwrite what we were trying to overwrite again. Then we will have 2 copies of 4A's on the stack at this point. Okay. Then we have EBP have the same value of ESP. Then from the function print secret point of view, its base, its saved EBP is at that address, 4 bytes higher than the valful function's stack frame. Okay. For that valful, it's saved, its EBP points to this place, right? But for print secret, the EBP will point to this place. Okay? So EBP plus 4 will be return address, but this will be the return address of print secret. Then EBP plus 8 will be the parameter of that function print secret. Okay. But you only have one chance to overwrite this. So what you are trying to overwrite will look like this. You have buffer here. Then you have the valful's saved EBP. The value doesn't really matter, garbage. Then you will have the return address, the address of the print secret. Okay? Then 4 bytes higher, you have another 4 bytes will be considered as the saved EBP for print secret. So the value doesn't matter. Then after that, you will have the parameters. In this case, will be just 1, 2, 3, 4, 5, 6. Okay. What confusing usually is this part. Why those 4 bytes don't matter? Why you should put the parameters here? Okay. So anyone here notice why we're doing this? How did we go to the function return, go to the function print secret? Did you call into that? You didn't call into that. You return to it. Okay? This is a same function. You're not supposed to return to it. You're supposed to call to it.
From the stack, basically.
Yes. Yes.
That's the data that's getting popped, basically.
Yes. Because of that, it was expecting you to call to it, so it will maintain a stack like that. But you didn't call to that. You directly return to it. That's why the stack will look slightly different. And you need to understand that. Okay. So in this case, the exploit will look like something this. So you try it. So this function will also give us the print secret address. We are trying to send two here. Oh, we don't know the size of the buffer yet. Let's take a quick look. Valful, the buffer is still at EBP minus E, so 14 bytes, same as before. So our exploit will look similar. We have first 18 bytes of garbage, then what is the return address? $18 bytes of garbage, then the address of this function, then another 4 bytes of the garbage, which will be considered by print secret as its own saved EBP. So that's why we have another 4 bytes of garbage. Then we will have the parameter for print secret, which is 1, 2, 3, 4, 5, 6, 7, 8. Then the whole thing we pipe into this program. Oops. So that's how we get the flag. Obviously, the parameter has to be correct. If the parameter is not correct, instead of 78, you print 79 there, you're not going to get the flag. You get I pity the fool, right? Of course, the buffer size must be correct as well. If you change this one a little bit, you will still get I pity the fool. However, like I said, there are many other ways to hack this program. You can directly jump to return to print print flag instead of print secret. So here, let's say we have print secret is at 1338. Print flag is at 1260. Okay. If we directly jump to that, here we change to 60, here we to 60. Okay. Then everything after this doesn't really matter anymore, right? Those bytes don't really matter. We should be able to get the flag, okay, because we directly jump to print flag. Is there any other place we can jump to? Inside print secret. Is there any other place we can jump to? Here, instead of at the very beginning, and we can still print out the flag. Many places actually. So you can see here is that comparison with 1, 2, 3, 4, 5, 6, 7, 8. If we do not want to give it a parameter, we just skip this. We just jump to here. Right? 13 for B, we return to here, then it have a call to print flag. Then obviously it will give us a flag. So that's another place, let's say 13 for B. For B, see, okay, this one works. If we change 1 byte, it may not work. 64 should not work. But 64 doesn't work. 64, we will jump to here. So we're not executing the call instruction. Instead of some kind of garbage instruction. I don't know what it is. Oh, not that one. Okay, not that one. Sorry. It should be. Similar idea. It should be this one. So when we do 64, 64 will be huge. It will be someplace random because it's this byte. What I wanted to do is 44 stay there. Yeah. For say, we still will get a segmentation fault because we will be executing from here. Then that instruction will not be called print flag. It will be an instruction, I don't know what it is, but it will generate a segment fault eventually. Does that make sense? Yeah. So there are many ways for you to capture a flag. So in the computation, in the final and the midterm, as long as you can capture the flag, it counts, okay? There is no right way or wrong way, yeah.
Was the address for print flag like really close?
Yes, they are close.
And that always be the case?
No.
This is
It is a case because I implemented this, and there are basically user-provided code. It's not the library, right? The library were at a little bit different address, but it doesn't really matter whether their address are close to each other. Even if they're not close to each other, you use the same approach to exploit. Yeah.
Just put way more. Characters that don't matter.
No, that part doesn't matter. You are overwriting the return address, right? The return address is 4 bytes. That 4 bytes can be whatever you want. That address can be the print secret address, can be print underscore flag address. It can be a library's functions address. Like C library provide all kinds of functions. One of the famous one is called system. Right? The system will allow you to provide a string, which is a command, and execute that. Right. That's why there is a classic attack called return to libc attack. That's basically how it works. Yeah. So you already learned how to do return to libc. It's just here you don't return to print flag. You just go to system and provide a parameter for that. Yeah. Yeah.
Instead of return to print secrets address, if we actually call that function, then why would it save EBP point to understand?
So first of all, we're not calling the function. When you call that function, the saved EBP it's a little bit complicated. It will not be 4 bytes higher. It could be lower or higher because it depends on how the function calling it is implemented, how its stack looks like. Yeah, there's no guarantee it will be at the same place. Okay, so we're done with this one. Okay, so this one is easy. Still C version, still a 32-bit version. Instead of 1 parameters, this function print secret now takes 2 parameters. Then it's your job to get this flag. This is overflow returns 3. Okay, I'll give you another 5 minutes to work on this. You want to do the 64 version of the return 2?
It was good to start up, but
Yeah.
I actually started. So
Okay.
could we just tweak this and just do
How do you do that? So he gave him several challenges. He wants to work on the previous version, return 2, but he wants to work on the 64-bit version. It's actually quite challenging. Think about it. 32-bit version, how you do it? The parameters are on stack, right? What is the difference between 32 and the 64-bit? Where are the parameters for 64-bit? They're on registers. So can you still overwrite them? They're in registers. They are not on stack. So you cannot provide the parameters to the function. That's why we haven't talked about how to do that. Yeah, we will talk about that in 3-4 weeks, actually. You know, a new technique. A new technique we do not talk about today. It's called return-oriented programming.
So I should put this.
You need to work on this. Well, I mean, you can work on version 2. If you got it, then I would be very happy, actually.
Trying to imagine the stack.
typo. Yeah.
Yeah.
Another typo. EB. It's not EB. It's BE. Because that's 1 byte. You don't reverse that part. Yep. Got it? Got it? Got it? Okay. Working on. Sure. Okay. You get it? That is the address.
And the secret address.
Yes.
So how do you know?
The program actually shows you. You
Uh,
run the program will print that out. You just run the program.
oh, okay.
Yeah. You don't need to debug. Yeah, just run the program. Yeah, it tells you.
Oh, okay. All right.
Yeah.
Makes sense.
Where's the second parameter? Okay, so here should be the address. Yes. We're missing the second parameter. How about you? Got it? Okay, so for this one, the exploit will be 18 bytes of garbage, then the address of print secret, then 4 bytes, another 4 bytes of garbage, then the value 1, 2, 3, 4, 5, 6, 7, 8, then the value of dead beef. Right? In total, that will be 8 bytes of parameters there.
I got a little confused when I did that beef first and then 1, 2, 3, 4, 5, 6, 7, 8. That's why.
Oh, the order of them.
Yeah, the order. So like
Yeah.
my script is like 18 bytes of garbage,
Mhm.
address 4 bytes of garbage, dead beef 4 bytes of garbage.
Yeah. The reason is in 32-bit, which one will be pushed down to stack first? This one will be pushed down to the stack first, actually. This one. Anyway, we also talked about there are many other places you can jump to. The same as the previous one, right? If you jump to, you skip those comparison, then you can still get a flag. Okay, so this cannot be used. This approach cannot be used for 32-bit version of programs because 32-bit of version of programs where we needed to pass the parameters use registers. So the technique we will use in the future is called return-oriented programming. Basically, we are going to look for some code sequences, small pieces of code sequences, usually 2-3 instructions. Those code sequences are already in the address space. They are not necessarily emitted by the compiler as intended instruction. It could be just some bytes, the last 2 bytes in a 4-byte instruction. Okay, and they are legit instructions there, and those instructions will help us to set up the values in the register instead of override the stack. Okay, it's quite complicated. We will do that much later in the semester. It's called return-oriented programming. So basically, the idea is still doable, just much more complicated. So since we can return to one function, with parameters. Can we return to many different functions? Okay. The short answer is actually we can. Okay. We can return to arbitrary number of functions, especially with the help of return-oriented programming. We can do whatever we want. But now, without return-oriented programming, we can still do a lot. Let's say this is the epilogue, before the epilogue of Valfu. It looks like this. We have a buffer here. Then maybe there's some padding. The compiler gave us several bytes of padding there. Then we have saved EBP. We have the return address. Then we have the argument 1 and 2, which was provided by the function that calls Valfu. So those are basically the parameters of Valfu itself, right? Now we have just one chance to override the whole thing from here to here. Then after the execution of Valfu, the saved EBP will be pointing to this place, and the ESP will move up. That's what we saw. That's why if we want to put 2 functions address there, we can actually. So the first function we want to return to, the return address we can just put here. Okay. The second function we want to return to, we can put the address 4 bytes higher, and they will not overlap with each other. The first function we return to, its parameters can be here. It will use this one as its first argument, this one as the second parameter. Then F2 we want to return to, we'll consider this one as its first argument and do not use this one, obviously. Right? So by using this approach, we can at least chain 2 functions in this way. But if those functions do not use parameters, then we can just put them address one after another, and we can chain them together. So the first function we return to, the address will be here. The second will be here. The third one will be here. If they do not use the parameters, you can keep go up there. Right? So let's say one example. There are 5 functions. Each of them will just call printf to print out something. And function 5 will actually also call exit. Okay. So our goal is to return to this chain of function. We'll return to F1, then F2, then F3, F4, and F5. And we have a vulnerable function Valfu here, the same buffer, 6 bytes. Get input from std in. The function print out the address. The main function print out the function address of all of them for us. The overflow return chain. So the idea of this is very simple. We just put them at their address one after each other. Let's go quick. So the buffer is still at EBP minus E14. That's it. That's the only information we need. Python 2. We need still 18 bytes of garbage, 14 bytes for the buffer, another 4 bytes for saved EBP. Now after that, we can have the address of the first function, which is d 62 556. This is the first one. If we just pipe this in, we actually will call that function, but it may not be able to print out things for us. Then let's just keep adding things here. We're going to add 5 functions here, right? 5 addresses. So second one, third one, fourth one, fifth one. First one 2D, second one 4A. Next one 67, 84, A1. So we can see it print out knowledge is power, France is bacon. Oh, we're missing is. Which one is? Second one is. So we can return to that twice. This one. Five times. So we will return to function 2 twice. So now we print out knowledge is power, France is bacon. We return to F1, knowledge. We return to F2, we return to F3, F4, return to F2 again, return to F5. And F5 will exit. Eventually we'll print out this. Right. So by using this approach, we can actually chain arbitrary number of functions together as long as they do not take parameters. If they take parameters, it will be a different story. We need to use return-oriented programming. Yeah, I give you another 5 minutes to just work on this one. The 64-bit version will be the same because there's no parameter. However, the address will be longer. That's it. Got it? No, this one doesn't have a flag. Yeah. This one doesn't have a flag, but this one is still a set UID program. And there is also a flag in the file system. So technically, you can exploit a vulnerability somewhere to get a flag, but that's not the intention. Yeah. Following? Did you get the previous one?
There's no flag, right?
This one, no flag, yeah.
Not doing 60.
Either way. Yeah. Okay. How you too? Here. Okay. You finish your homework? Okay. Okay. You also knew, right? Okay. Yeah. Did you watch the video of the first 2 weeks? You need to watch the videos because there's a lot to digest to get here, even to get here. Got it, right? So this is what you'll try to overwrite, right? This is a sequential overwrite. So you write buffer, put garbage there, then you put garbage as saved EBP, right? Then you put the address of return secret here. Those garbage AA, the value actually matters. That's what I'm trying to say here. The value actually matters because those values will be eventually used again to move to EBP, then pushed onto the stack again. That's why there will be 2 full A's here actually. No, that pushback is at the prologue of print secret. We reached there because here, evolve you returned it. Evolve doesn't have the address. The address is on stack, and you overwrite it. That's why after Volfu, we are executing print secret. Yes. Got it? Not yet?
Put 18 bytes.
Which one?
Address
Okay.
on one pack.
Mm-hmm.
And the address of the
Mm-hmm.
4 bytes.
Yes. Yes. Maybe. I don't recall that part exactly, but I need to look at the disassembly later to check out what's going on there. Yeah. Mm-hmm. Yeah, exactly. Right. The rightmost get pushed first, so it will have a higher address. So that's why dead beef has a higher address. Higher address means in your exploit, it will go there later, right? Mm-hmm. Yeah. You guys got it? Yeah.
64 bits.
Yeah.
And the buffer size is 6
Yeah.
bytes.
Mm-hmm.
And then this is 6 bytes. Yeah. There should be 8 bytes. Yes. There should be 8 bytes.
So what? This 8 bytes is, yeah.
It's my bytes.
Yes. So how many bytes you are giving here for return address?
That
14? No. So these are 14 bytes, right? Those are garbage. This one is not a garbage. You need to put the right address there. Yeah. If you finish the 32-bit, you can work on the 64-bit.
there be storage registers. So it's 14.
Okay, that's right.
And then I started pushing in all the addresses of the functions.
The problem here is how big are those addresses?
Oh, these are each 6 bytes. I'm pushing
What? How many bytes?
each is 8 bytes.
Why? It's not 8 byte. The address in 64-bit is 8 bytes. The reason you're seeing a smaller number there is because the leading zeros are not showing.
So I have to put leading zeros.
Yes, yes.
I'm only pushing 4 bytes. Got it.
Yes. Yeah, you're missing.
Got it. Got it.
Mhm.
And
So
the 14
basically
euros.
what you did is this one becomes an address.
Got it.
Then it go to middle of nowhere.
Yeah,
Yeah.
so I need
Mhm. Got it? Cool. We were keep moving forward. So this is the very first control flow hijacking, and we are going to do a lot of control flow hijacking this semester. Let's revisit this picture because, like I said, many things we're doing fall into somewhere this picture, right? So first of all, the first step here, what we're doing is we make a pointer go out of bound. Okay. So for what we just did, which pointer we use? We make which pointer go out of bound in this attack. The reason we want to make a pointer go out of bound is eventually we are going to use that pointer to write something, right? Which one? The buffer close. The buffer is a fixed address, right? So it's actually a pointer somewhere in that gets function, and it's supposed to be just pointing to something within the scope of buffer, but that pointer goes beyond the buffer. Okay. Then from there, we use that pointer to write something. We write things beyond the buffer. We write to the return address on stack. And that return address is a code pointer, right? It's supposed to point to a piece of code. So that's the first. The third step, we use the first pointer to modify a code pointer on the stack. And we are changing that code pointer to the address of other functions. So here, we can also change the pointers to the share code or gadgets. That's what we're going to do in a moment. Then, eventually, that return address, that code pointer, is used by a return instruction. Okay. Which return instruction was it? We overwrite that return address. That return address is a code pointer. Okay. That return address is eventually used by a return instruction. Which function's return instruction that is? Is it gets? Is it valful? What? Okay. It's actually the return instruction that use what we override is the valful's return instruction. Okay. It returns to print secret. Of course, when you have multiple chains there, then it's different. Okay. In that chain example, the return address was the return instruction first was valful. Then second, you use the return instruction of F1. Then you use the return instruction of F2. F2 returns to F3, right? So that's a chain. Then by doing that, the CPU start execution the function, print secret, print flag, F1, F2, whatever. So we are changing the control flow. That's why this is a control flow hijacking attack. Okay. If we didn't do this, the valful is supposed to return to the main function. Main function is supposed to return to the libc start main function. We changed that control flow. So that is basically how we can change the return address. Now we're going to do something much more powerful and generic based on this. We're going to overwrite the return address, but now we will not return to a function in the address space. There will be no print flag function or print secret function in the address space anymore. But we still want to print the flag. Okay? So we're going to create code there to do that. So we're going to return to our own share code. We're going to use this example. The example is actually quite similar to the previous example. The only difference is there is no print flag function anymore. We are saying bye to print flag functions forever, okay? No print flag function anymore. We have a buffer, 40 bytes in C code. We still have the same bug, gets there. So there's obviously a buffer overflow. The buffer is slightly bigger, which doesn't really matter. Even if I give you a very small buffer, we should be able to do the same thing. Then just the val foo, print out IPD the foo. That's it. Very simple function. No print flag function in the address space. We're going to exploit this. So the goal here is similar. We're going to overwrite the return address, and we are going to inject some code there. We're going to put code in the address space, and that code will either give us a shell or just print the secret for us. Okay, that will take just 10 instructions. 20 instructions, not many instructions. We're going to code that part. Then the return address, we're going to override it to eventually point to the code we inject there. So it will inject our code. That's a simple idea. Okay. Let's say the stack still looks like this. We have the buffer. We have saved the EBP. We have the return address. And we can override the whole thing. The first attack we're going to do is we're going to put our share code inside this buffer. Then this return address will be modified to point to this share code. So when this val foo function returns, it will execute the share code. But everything is on stack, okay? So here we assume the stack is executable. Of course, we can put the share code in other places. If the buffer is big enough, we can even put some nops. Nop instruction doesn't do anything, it will just go to the next instruction. Okay. Because to achieve this, we need to know exactly where the share code is. Sometimes it's hard to get. So we can also put a little bit of nops there. If we jump to any nop instruction, it's just 1 byte, and it will just go to the next instruction. So if we jump to the middle of this nop region, or we call it nop sled, eventually we will keep executing one by one. We will keep executing, get to execute share code, right? Or we just put share code at a much higher address than we can have a lot of thousands bytes of nops there. So make our job much easier to guess. So the nop, there is a specific instruction for it. It's just it's called a nop, and the hex value of that is just 90. That's one instruction. Then go back to share code. We kind of talked about this in the very first class. Today we can use this share code, 28 bytes. It has some limitations, but let's take a look again. This is only 28 bytes. It makes 2 system calls here. The first one here, int 80. Another one, int 80. The second system call doesn't really matter. So this share code can be actually smaller. 23 bytes will be the same. So let's take a look what this is doing. And then you will understand why I say the second system call doesn't really matter. So in the first system call, the AL, the register AL, which is part of EAX, has the value B here, right? So B, if you go to B is 11, if you go here, this is the system call exe CVE. The second system call here, EAX, we have inclusive OR operations on it. So it has a value of 0. Then we increase EAX, so EAX has a value of 1, right? Then that is a system call number. The system call, so basically it's exit. Okay. So we're making 2 system calls, exe CVE, then exit. Okay. So many of you take computing systems. If this system call is successful, are we going to execute this piece of code? No, right? So the first system call, exe CVE, will replace the current process with a new program. So after it is replaced, we will not come back to execute this. That doesn't exist anymore, okay? So these 3 instructions will only be executed if this system call is not successful, okay? When this system call is not successful, it will keep executing, it will have a return value, then it will exit. Okay. So that's why those 3 pieces of code is only for the attackers to gracefully exit, to hide I'm attacking, to not show segmentation fault or whatever in the terminal. So technically this part is not needed. Then the very first 23 instructions are executing this system call. We discussed this in the very first class. We are executing bin sh, which is a shell. It will replace the current program. The current program is whatever you have there, whatever you are attacking. Return overflow forward. Yeah. So those are the parameters. So we can skip that part. Little bit of animation here. The first instruction, get EAX 0. So EAX will have the value 0 here. Then push EAX. Then we get 4 bytes of zeros onto a stack. The reason we're doing that is we're trying to create a string on memory. Stack is memory. Then we push those 8 bytes there, and those 8 bytes maps to a slash bin slash sh. Like I explained before, those 2 slashes will be equivalent to just 1 slash. Right. After that, we move the string's address to EBX. And the string's address is what ESP points to because we pushed it. Right. So EBX now have the string's address that is required for the system call. Then ECX will have just 0, which is now pointer. Then EDX is also 0. Then EAX is 11. So now we have EAX 11, the system call number. EBX points to the string, which is the program we want, the path of the program we want to execute. Then ECX, EDX are for different parameters. We don't care, so just set as 0. Then we do the system call, exe CVE. So now if this is successful, we should have a shell. And we will not return to execute the rest of the 3 instructions. But if this is not successful, this int instruction is basically an interrupt. This will return here. It will not replace the current process. It will return here and keep executing. Then we just want to clean up. We want to gracefully exit. That's why we have EAX as 1, which is a system call exit. Those other 3 registers, the value doesn't really matter. Okay. Then we make the system call int 80. Then it will just exit. That's it. So this is our vulnerable function. Very simple. No print secret. So let's take a look how we do this. The buffer, if we look at the disassembly, we'll see that the buffer is at EBP minus 30. That's 48 bytes. So we ask for 40 bytes at a C code level. The compiler actually gave us 48 bytes. How big is our shellcode again? 28 bytes, right? Which means we can put the shellcode in the buffer. big enough to put it there, right? So we can put share code there at the beginning of the buffer, put some garbage, then save the EBP, garbage, then return address. Right? We can do that. We can also put some knob set, which is 90 there. We can also put at even because we can overwrite a very large region, so we don't need to use the buffer. Buffer, we just put garbage, save the EBP, garbage, return address. We will set on some address, then we have a huge knob set. Then eventually that goes through to our share code. Right? So we can just try that approach. So here, if you want to go with this approach, you need to know exactly where the share code is because you want to execute at the beginning of the share code, and the address needs to be right here, which may not be easy. We can debug it to get some idea where it is, but it's not necessarily the accurate address. So we will just go with the third approach. We have a huge knob slet, and that'll make sense much easier. Okay, let's try this one. First, we will try something I call shell share code. Okay, this share code is a term developed maybe in the 90s. The goal of it, originally, the goal of it is to return a shell to the attacker so the attacker can do whatever they want. But think about our attack here. Do we really need a shell? Our goal is to get the flag, right? The code we want to execute there, as long as it can read the flag to us, we're happy. We don't really need a shell, right? So that's why, but we still use the name share code. So when I say share code, is a share code that actually gave us a shell in this case. This is a piece of share code we are going to try. This share code will not give us a privileged shell. It will give us a shell, but not privileged. That's because Linux kernel have some new defense to downgrade new programs privilege. But we have another version which we will keep the privilege. So this one is exactly the same as the 23 bytes of the previous one. Very simple. It will be able to give us a shell. Let's see how it works. We will try something like this. This is the overflow 4. Overflow return 4. There are many different versions of overflow 4, different levels of defense there, which you need to defeat later. Let's see this one. Let's do this one first. We'll do a dump first. obj dump. B Intel. Let's confirm the address of the buffer first. This is lawful. From here, you can see that the buffer is at EBP minus 30. Okay. So the buffer is 48 bytes in decimal. So, let's see. Oops. I need to fix this a little bit because of the. I need to fix a white space here because I copied from slides. Is there else I need to fix? It's good. So first, we have how many bytes of garbage? 48 bytes of buffer, another 4 bytes of saved EBP. So that's why you can say here, I have 52 bytes of garbage, right? Then after that, we should have 4 bytes of address, which I don't know what it is. But it will be somewhere on stack, right? Because we are injecting the whole thing on stack, injecting this to buffer. So I just put a random address there. Should not work. Then, after that, we are trying to have a knob slet, right? A knob slet is just a huge instruction sequence of null. It doesn't do anything. It will just go to the next one. The idea is as long as we execute to the middle of that, eventually it will lead to our shellcode. So this one, let's do maybe 2000 bytes to make it big. Okay. So after that, we have our shellcode. I just copied that. 23 bytes of shellcode. Okay. You can directly use this. Now after that, because this is shell, we actually need to keep the file descriptor open. That's why we have a cat here. Okay. Anyway, let's try this. Ooh. Not that lucky. Now, we only need to figure out what address this should be. Okay. This should be the address. This should be the address pointed to our offset. Make sense? Okay. Let's try where that is. So how do we find the address? DDB? Yeah, we can debug. Or what if you are attacking a remote server? Where you cannot GDB, cannot debug. What do you do? Just guess. Just keep trying. You send out hundreds of requests. You just need one request to be successful, right? Okay, now let's just GDB this. We debug this. We set a breakpoint at valful. Then we execute this. Then we just examine where our. We just print our where the stack is. See the stack right now. Well, inside the valful, okay. I set a breakpoint at valful, beginner valful. Then I run the program. So now we hit the breakpoint at valful, which means ESP should point to the beginning of the stack frame of valful, right? Then I just print out the value in register ESP, the stack pointer. P is the command to print out, and it has this value, FFD6 5C, somewhere there. So, which means, however, this address actually, because we're in GDB, GDB will push a lot of more things onto the stack. So this address may be lower than the address you have when you just run the program without using GDB. So this address may be lower. So we probably want to go be higher than that. But anyway, give us a place to guess. So strike off is too small there. E6. This value doesn't really matter that much, right? Because if I change this value, no matter I change to 0 or FF, I'm just jumping between 256 bytes. Because this is the last byte of the address. However, our lock set is 2000 bytes anyway. So this doesn't really matter that much. Let's try. Syntax error somewhere. Let's see, where's our syntax error? Oh, somehow here. I add a slash here. So that should be 90, the not instruction. Try this again. Doesn't work. Okay. Let's make it a little bit higher. Because GDB's address will be a little bit lower, so let's move up first. I think move up will have a better chance. So D6, we just moved to E6. Oh, that's probably too much. Maybe DD here. Oh, it works. We got a shell. See? I just changed this byte. Of course, there are some other addresses, a lot of other addresses we can change, and will also give us a shell. So DD works, then DE probably also works because our knob set is 2000 bytes. Right? Also works, right? Our knob set here is 2000 bytes. Let's see. Now we have a shell. What do you want to do? You want to carry the flag, right? Let's see if we can do that. we catch a flag. We get a permission delay, okay? Why is that? Who am I? We are actually CTF, we're not root. Okay. What happens here is we successfully get a shell. On Linux kernel, we're downgrade our permission to who we are. Where we attacked a setuid program, but when we create a new program, Linux kernel will downgrade us our permission. This can be easily changed. This can be easily addressed. So that's why I say this piece of shellcode doesn't really work. Okay, so what we needed to do is we only needed to make several more system calls. Before we call exe cve here, we needed to make another system call set real and effective UID again. Okay, this is a set UID program. We can do that. We just confirm that the new program we are going to create will still have the set UID privilege. So it will not drop the root privilege. So this is the new piece of shellcode, which is a little bit longer. We don't have the exit here, okay? But this one is already 25, so that's 37 bytes. Okay, so that's 37 bytes of shellcode. Let's try this. I need to remove the zeros there. There's one new line there. There's another one. Oh, those two. So the address we tried there was this byte doesn't really matter that much. This one we tried DDDE there as an FF. Upstairs we use 2000. You can make it even bigger. I think the share can take thousands bytes of input. So I'm not sure 5,000 it can still handle. Let's try. When you get this error, means the share we are using right now cannot handle that much. So 5,000 is too much. 3,000 bytes. Okay, now it has a different address. Okay, let's go back to 2000. Yeah. So when we have 2000, actually it has this address works. When we have 3000, we'll probably need to, should we move up or move down? When we have 3000 there, we're copying more things there. Maybe we can move up. Anyway, now let's say who I am. So now we are root. Now we will be able to catch the flag. So this is actual shell. You can do anything here. You can do a wget, right? You can download things from the internet, right? And as a root, you can do whatever you want. So this is a very simple vulnerability, and you get a full control of the computer now. Okay. However, we do not really need a shellcode, like I said. Our goal is just to catch the flag file. So here we have a simpler shellcode. This one is a little bit long, but this can be significantly reduced, the size of it. We will have a shellcode workshop before the midterm. And in that workshop, your job is to make this piece of code much, much smaller. When I look at this, I think there are, how many bytes we're talking about? 2D, okay. So that's almost 50 bytes? Yeah, 40 something bytes, okay. In the shell code, you need to reduce this to, I think one of the challenges I have is 8 bytes. We're going to reduce this to only 8 bytes. I have seen someone develop a challenge like 4 bytes. Just the 4 bytes, you can make this work. Okay. Yeah. Anyway, let's try this. This one, what actually it does is, first of all, we still have an exit here. So this 6 bytes, you can get rid of it. Doesn't matter, right? This one makes 2 system calls. Forget about the exit 0. We can delete that. It makes 2 system calls. The first one is open /flag, which is a string. So that's an open system call. It will open a file. It will give a file descriptor. Then we are going to send the content in that file descriptor to file descriptor 1. The send file, the first parameter 1, that's where you want to send it. So std out, file descriptor 1, which is the terminal. So we're going to send that to the terminal. So this is a little bit different from how usually you write a C code. Usually when you write a C code, you open a file, then you read a file, then you write it to a terminal, right? You open, you read, you write. But here, that actually takes 3 system calls. Even though you are using a function, but those function eventually leads to a system call. And it also takes a buffer there. Open, then you use read system call to read the content of that file to a buffer. Then you write the content at the buffer to std out. You make 3 system calls. So here, by doing this, we do not need to create that buffer. Kernel will create that buffer, and we do not need to make 3 system calls, just 2 system calls, open and send file. That's why we prefer this approach. Let's say we're sending 1,000 bytes. So in my example there, I write 1,000 bytes, but I remember in my binary, it was not really 1,000 bytes. So I believe this is the send file system call. You can see here. Let's say 1, 2, 3, 4. The 4th one is probably. So this is probably the system call number. BB is the number. Yeah, it's here. I think this is the size. 64. In my share code, I actually only put 100 bytes, not a 1, because I know the string is not that big. Right? Okay, so let's try this. And because we are not getting a shell, so you can see this command here, we don't have that cat anymore. We don't need a cat. We don't need to keep the std in open there. Let's try to use the same number of sled. So the previous address should still work. FF. And another thing you notice that in this share code, we do not have 0. Okay? We don't have the null byte. The reason is that the vulnerability you are exploiting here, you are attacking here, may be a string copy. And a string copy will stop when you say 0. If you have a 0 here, then it will only copy half of your share code. So you will not be able to execute the full share code. That's why we intentionally avoid using 0 there. That's why when we say something 0, we use exclusive OR that register instead of moving 0 to that register. Right? Okay, this should work. Yeah, it works. It gives us the same flag. The address, obviously, can change this. This byte doesn't really matter. We change it, whatever it should work, I guess. Well, not the S. That's not a byte. The E works. The second byte is different story. Tried D0 before, maybe didn't work. Yeah, D0 doesn't work, but DD works. D9 also works. The obstinate, we can make it even bigger. Let's try 35. 35, so that work. 5, work. Should we move lower? Even higher? E doesn't work. We try D, we try E. Let's see. Even lower? Doesn't work. I'm not sure. Maybe this one's too big. Yeah, okay. 25. 100 is R. 2000 is R. Lucky number today anyway. We just stick with that. Okay. So you see, we do not really know where exactly our share code is. We just have a rough idea where it is. And we start guessing there. Of course, you can write a script to guess. And eventually you will find out. So no matter what number of threads I have here, eventually we'll find out good number for that. Okay, 64-bit. How is this different? If we want to attach 64-bit version of the same program, what do we need to change? First of all, do we need to change the share-code itself? You said no there.
Yes.
Yes. Okay. That's right. We do need to change the share-code. Okay. Because now we are running 64-bit version of the instructions. The parameters are different. To set up the share-code parameters, the system call parameters, they are different. So this is the same code. Actually, the buffer will still add that address, EBP minus 45. The share code here in 64-bit version can be actually smaller because in 64-bit, there are instructions for us to do something like this. RIP plus bin sh. This is not possible in 32 bits. Several of you probably remember this. This is what we did in our first assignment in computing system class. But we didn't really teach you guys this in that class. But many students come up with this magically, so we talked with them about large language models. Yes, many of them. So this is how we can generate a similar share code. We can see that part and directly go here. So here the same thing. We just open and send the file. It's just everything is 64-bit. This one is 0? No. I don't see any 0 here, so it should work. Oh, we need to get the address first. Program doesn't tell us, so we just debug this. Set a breakpoint at val-foo. That's what we did before. We execute this, we just print out RSP. We'll give this address. Then let's say, we can check this, but probably it's correct. 56. Yeah, the buffer is still 48 bytes. The 8 bytes of saved RBP, that's why 56 bytes there. Then address will be, try this one, E5. How many Fs are there? That's 6 FF, 3 FF, then 7F. How many bytes are there already? 1, 2, 3, 4, 5, 6, 7. Okay, need another. Oh, so now we have 2 zeros. That may change things. Solid. What are we missing here? Oh, there's another 0. Here, there's a white space. We need to remove that. Okay. Illegal instructions. We're jumping into illegal instructions, which means this address is not correct. Let's try to make the lobset a little bit bigger. Segmentation for it. To this one, to EE. Port. Yeah, this may take a while. EE there. And maybe the EE there. Want to move up. We started with E5. So how many bytes between E5 and EE? E is 13. 5, then there are 800. The 8 times 200, that's actually probably 1600. Okay, that's quite a big jump actually. Let's try E8. Oh, it works. So E8 actually works. So from EE to E5 is actually a big jump there. From E5 to EE there, right? Because this one is, this byte is 256. Here is probably 8. Then 8 times 200, that's 1600. Our lobset is only 2000, so probably we jumped out of the lobset. That's why I make the jump a little bit smaller. So that's why how we get the flag here. Okay. Let's keep going. Of course, we also have a share code version for that. Then you can try this later. That will be your homework. Okay, so what do we have learned so far? Now there is a buffer overflow. We can overflow the return address. We can return to wherever we want to return to. Then we are trying to inject some code in the address space. Then we return to our code. So this is also called the code injection attack. So the challenges we overcome, first of all, we don't really know exactly we should return to. We don't know the exact address. To increase our chance of success, we add a huge lobset there. Okay. Then we started guessing. By adding that lobset, we increase our guessing success rate. But without that, technically, we still should be able to guess. We just write a script to keep guessing. Eventually, it will work. Another challenge we had is for the share code, when the setUID program is replaced with a new image, the new process doesn't inherit the root privilege. We address that by adding another setREUID system call before the EXE7E. We can actually put the share code at many different locations. So right now we are putting share code on stack. There are many different ways for us to put them on stack, actually. Command line arguments eventually go to the stack. Even if your program doesn't use command line arguments, your share will copy that command line argument to your program. Your program just doesn't read that. So it will be injected there. Environment variables will also be onto the stack. That's a global environment variable. When you create a new program, your share will copy that environment variable to your address space. It's also on stack. So the question here is why the stack should be executable? Why should you put code on stack anyway? Is there any reason we should put code on stack? Any legit reason to put code on stack? Not really. Okay. Code should go to code section or other sections. They should not be on stack. So that's why 20 years ago, CPU introduced new features to make a memory region writable, but not executable. Okay. So stack obviously needs to be writable because that is for your local variables. Scratch memory should be writable. But if we make them not executable, even if you inject code there, even if you return to that location, your CPU will not be able to execute that. Right? So that is one stop. Okay, so usually when I do research, I like to list the conditions attackers depend on or need to pull off an attack. I like to do that. That's a training, a practice for us to come up with new defense ideas. So in this example, let's say the attacker first needs to have the ability to put the share code onto the stack. And that ability is given by us because the program is vulnerable. It has that get function. It has string copy function or other vulnerable dangerous functions. Because of that, it gave us the ability to put share code onto the stack, copy to there. Then obviously the stack is executable. Also, we should have the ability to override the return address, and eventually that return address is used by a return instruction. And eventually that return no matter where that return is, where that return to, eventually it gives control to our real share code, not just the lob select, right? So as defenders, if we take out those conditions one by one, or just one of them, we create a new defense. It will not be a perfect defense, or perfect defense may not even exist anyway, but it will raise the bar for successful attacks. And sometimes, some of the defense, they look very naive, they can be bypassed, but because they are very cost effective, computational wise, it's very cost effective, they are actually the ones deployed. There are some defense, in theory, they are very good, they are perfect, but they are very, very expensive. They make your program run 10 times slower. No one will ever use them. The ones we are using, they are not perfect. They can only handle some cases, but they are deployed in real world. So let's take a 10 minutes break. Then when we come back, we will learn how to inject share code in other places.
No, we don't say that actually. I know it's hard to record. That's the essence question as well. Yeah, I'm just like trying to figure out what tools I want to have.
Yes. Discount in the stack, you have to override that. Because the free is not mentioned out here.
Here is to still inject the share code to the address space. In particular, we want to inject that onto the stack. And there are many different ways to do that. First, we can put the environment to put the share code in just the environment variable. The OS will copy that to the address space. We can also copy that to the command line argument, even if the program doesn't take command line arguments. So why they are on stack? Those two things, command line arguments and environment variables. Why they're on stack? So when you write a C program, your main function, the main function, from your developer's point of view, all this program is compiled into an executable. The entry point for that program is not main. Usually it's underscore start. So that is the entry point. And that one is also, the address is specified at the header of your L file. Executable is the L file. The header of the L file will tell us where is the entry point. Usually that is the underscore start function. Then that underscore start function will eventually call the underscore libc underscore start underscore main function. So that is the C library. Function eventually calls your main function. So when your main function returns, your main function doesn't do exit directly. Your main function also returns, right? So your main function returns to underscore libc start main, which will clean up everything. Then it will eventually make a system call to exit. So, which means before your main function, the C library and other libraries has been setting up a lot of environment for your program. And that includes the command line arguments and the environment variables. You can use the env command to say what kind of environment variables have already been set in your computer. Let's say this one, or just do an env. You can say there are so many environment variables already set there. The default share we're using is being share, hostname, the current directory, the username, for display, what kind of colors, all kinds of things. And obviously you can also share, you can also set up environment variable. And those will be pushed onto the stack. So let's say we have a stack layout challenge here. So this stack layout program will just print out what is on the stack, and we can give it command line arguments. Let's say this command 1, command line 2, command 3. I'm trying to print, I give it 3 command line arguments. Typically there are 4. The name of it, the first command line argument. Then we have C1, C2, C3. So if we just print out the data, we can say, this is the command line argument, another command line argument, another one. Then after that, you can see what we have here. We have the environment variables as well. Right? Our program didn't do that. the shell, the OS, put them there for us, the environment variables. What I actually have on the stack is this. Let's say this is high address, this is low address. Main functions stack frame, and the main function has 2 arguments. So you will have argc. Let's say the example is stack layout hello world. So there are 3 command line arguments. That's why argc is 3. Then we will have an array of strings, right? An array of strings address. That's why we have argv0, argv1, argv2, until we have a 0. This is an array of addresses of strings. And those addresses, because they are address, they are pointers. They eventually point to the command line arguments. And the command line arguments will be somewhere on the stack, pushed by the shell or whatever. So that will be the string of the program itself, which in this case is stack layout. Below it will be word. Then after that, we have another array of environment variables. So usually when you program the say main function, you don't write this part. Okay? Usually when you program a main function, you only have 2 parameters, the argc and the argv. There can also be an environment v there. Usually you don't use, but it can be there. That is the main function's prototype. So we have another array of addresses, which are the addresses of environment variables. And each of them is a pointer where eventually point to the environment variable somewhere. So to confirm that, we can just debug this program. Let's see. We debug this program, we run it, we give it multiple command line arguments, and try to do 5 here. Just set a breakpoint first. Set a point on main first. Then we run this. Okay. At the beginning of the main function, and the stack pointer is at ESP. So if we examine this address, because we give some strings there, right? String are command line, argument strings, and also environment string. So we just examine, let's say, 500 strings at this stack address. So far, we haven't been running any of the main instructions. Even if the main function print out something, does something, we haven't been running those code. So we haven't been using the stack, the main function. But I want to show you that even at this moment, there are many things already on stack. So if we examine just the strings here, we see some garbage. Some of them may be just address, pointers. That's why we do not say a string. But eventually we keep doing this. We're going up. You can see the address, we're going up. I'm trying to say here, what do we say here? Arguments, we say here, right? That's the first command line string, the second, the third, all of them. Then after that, what do we have? So between this, probably we have a 0 there. Then this is the environment variables. Okay? We saw that when we were outside of GDB, when we do a array there. So see, we say the environment variables. So those were actually pushed onto the stack for us. And keep going up, then probably those memory regions were not met. That's why we do not get it. So because of that, we can utilize this to our shortcut. So overflow return 5. The buffer, in this case, is only 4 bytes. And you can only input, the vulnerable function here is fread. And fread will eventually read the 18 bytes in this case. I remember f-read were actually append two bytes at the end, so typically you only read 8 bytes. Yeah. So let's say f-read. F-read will read from the stream and the store into the buffer, and it will add a new line. Remember, it will add a new line. Probably add a lot of bytes as well. And the line is ASCII, not ASCII. Hex value is A, then end of line is 0. So it actually adds 2 bytes. It adds 2 bytes in. So this is a disassembly. F gets buffer is at EBP minus 8. Okay, we ask for 4 bytes. Compiler actually give us 8 bytes there. So the buffer is the save return value 4 bytes. That actually will be 16 bytes. Okay. Then f-read will also append hex value A and end of string 0 there. Together, that's 18 bytes. And fgets will only write those 18 bytes. So what does this mean? It means if you want to inject a shellcode here, if you want to inject shellcode through fgets, you can only put shellcode here and 8 bytes of shellcode. Okay, that's it, which is possible. Okay. But that's not what I want to show you today. Okay. So we're not going to do an 8 byte shellcode today. Instead, we just put shellcode in other places. Okay. Environment variable. So command line arguments. The first one is to environment variable. A new environment variable. Whose format is the name of the environment variable, the equal sign, then the value of the environment variable. We are using dollar parentheses here to run a command. Then the output of the command will be the value of the environment variable here. Excuse me. So the name of the environment variable doesn't really matter here. I just use S code, means share code, but it doesn't really matter. Then to code which generates the share code. So let's do 2 bytes of offset here. Still missing the white space somewhere. Do you guys see a white space? Oh, missing a parenthesis here. Okay. Okay. Now we do an environment variable. S code. That's our share code. Not every byte of our share code is printable. That's why you can only say at the beginning there's some printable strings. Maybe the 2000 bytes of NOPSnet is actually not printable. So that's why it's actually here, not printed. Some of the bytes are printable, okay, but it's obviously much, much longer than this. Here you see it's just 15 characters, but actually it's 2000 bytes, more than 2000 bytes. How to get the address of that? We actually provide you a program to do that. It's called get environment variable S code. This will give you the address of this environment variable for this program, actually. So if you run a different program, It may be slightly different, but there will be a similar address. However, even for this program, this address you are getting is the beginning of the environment variable. Okay? So this whole thing is environment variable. So where is the beginning? The beginning is S code. Okay? It's not the value of it, it's the S code of it. Okay? Which means if this address is correct and you start executing here, it's not your shellcode. Okay? You still need to add some value to this to jump into the middle of the null slip. Then the environment variable is already here, then the attack will be obvious here and simple. Take a look. Waffle with fgets. The buffer is at EBP minus 8. Okay, that's it. That's all the information we need. It's fgets, which means we will pipe into this. How many bytes of garbage we need? Buffer is EBP minus 8 bytes.
8.
Huh?
That's 8 as well.
Because this is 32-bit. We still need to override the return address, right? So we need the 12 bytes of garbage. Okay. After the 12 bytes of garbage, what do we put here? That's our shellcode address, right? Where is our shellcode? It's in that environment variable, which address is somewhere near that. So let's say, let's just do FF D6 FF. That's it. If it works, it works because we put the shellcode in environment variable. And we jump to that. So in this case, we didn't directly inject the shellcode in a command like what we did before. We put the shellcode in environment variable. Okay. So this is one way to do it. So that get environment variable tool we provide for you is just as simple as this. Okay. It will look for it will use this library function get environment variable to look for the address of that environment variable and just print it out. So we can skip this one. We're not. Then how do we do command line? Let's first remove that. How do we remove environment variable? Anyone here know? Delete? No. Unset. Okay. Unset. Let's code. I think it works. Let's try to get an address. Okay, that's right. Unset. Okay. So now we don't have the environment variable. We still, this is our shellcode. We just give this shellcode as, we just give this as a command line argument. No, this is not enough. We still need the previous one. This one. Okay, good. Something like this. To remove this. Okay. The program still takes input from std. That's why we are piping something into it. We're piping similar exploit, 12 bytes of garbage and the address to overwrite. Now we are putting our shellcode in the command line arguments. Even though this program itself doesn't use command line arguments, it doesn't look for that. But if you put it here, share where. So change the offset to 2000. Let's see if it works. No, I'm missing something here. Oh, missing that parenthesis. Okay, do it again. Oh, we're very lucky. Just one time it works. Yeah, the same address actually works. I didn't change the address, but it works. So those are the two places on stack we can inject share-code. There are many other places as well. Yeah.
In the second case, the return address would be of the command and argument, right?
Yes.
The argument that you use first.
Yes.
And in this case, it's almost similar as the environment variable.
Yes, because in the previous case, well, before we inject this thing, you can see that the command line arguments, they are actually short, not many bytes. The environment variables are also relatively short. We only have like 10, 15 environment variables. Now we are injecting something thousands of bytes. That's why we get lucky by just using the same address, because it's much bigger than what originally was there anyway. Okay, so finally, what we did here is we modified the return address, make it point to a share code, and we somehow get that share code into the address space of this program, and eventually we were executing that share code. It's actually here, more complicated. Execute the share code, not executing the function. That's actually all I have for today. Any questions? Homework 3. Here, and I also give you guys, which I didn't show you guys, which is overflow setup. But there are many more challenges on there. They're not necessarily on our platform, are not necessarily in the homework, and I do not demonstrate them in the class, and you can also work on those. So I think that's the only one. Everything here, I demo this one, all this one demo. Oh, there is another reverse engineering one. So we still have some time. You guys can start working on those. Maybe starting from task 8 or 9, since we didn't talk about them in the class. We'll walk around to help you guys.